on confidence intervals for the mean. This lecture follows in close analogy to lecture 19, confidence intervals for a proportion, where we use the sample proportion to estimate the population proportion. Here, we're going to use the sample mean and some other information to estimate the population mean. To do that, we'll have to remember in lecture 17 when we described the distribution of the sampling mean. So, in lecture 17, we had a numerical variable, its population mean, the average over the whole population of the numerical variable, mu sub x. Its standard deviation, its population standard deviation, was sigma sub x. And we imagined all possible samples of size n from the population. We had to make some assumptions. We assumed that the samples were all simple random samples. We assumed that the population was at least 20 times the sample size, so we could treat the variable as independent, the different elements in the sample as independent, and we assumed the 0, 15, 40 rule. Remember, that means that either x was known to be normal, or the sample size was at least 15, and the distribution of the variable x was not too skewed, no major outliers, looked okay, or, the simplest one, the sample size was more than 40. So, if any of those are true, then we were able to conclude that the distribution of x bar, that is, if you look at each sample, calculate the sample mean as a number for that sample, all those numbers will have a normal distribution with a mean mu of x and a standard deviation sigma x over the square root of n, which we called the standard error, because x bar is a sampling distribution. That was all review. Now let's think about the problem at hand. So suppose you want to know the average cost of the last haircut for all American college students. Population is college students. Variable is the cost of the last haircut. We want to compute or estimate the population mean or average. How would we investigate that? We would take a simple random sample, let's say, of 50 college students. We'd ask them all how much their haircut cost, much like I did with you on the first day. And let's say that we got a sample mean x bar is 35 and a sample standard deviation s is 30. Those are both measured in dollars. So when we ask about a confidence interval, we're asking what are plausible values for the population mean, which is to say the average cost of all American college students' haircuts. Well, we know the first part of that. We know that x bar, the sample mean, is the point estimate for mu sub x, the population mean. So in our case, the best guess that you can get from the sample for mu sub x is 35, and that seems reasonable. To make it a confidence interval, we're going to have to use the same tricky approach that we did in lecture 19. We start saying we know sigma and mu, and that all the assumptions are met, so that means that x bar has a normal distribution with a mean mu of x, standard error, sigma x over the square root of n. What does that make reasonable values of x bar look like? Well, we know that in 95% of such samples, x bar will be within 1.96 standard errors of the mean. That is, within a distance 1.96 sigma x over the square root of n of the mean mu of x. I'm using little x bar because now I'm talking about individual samples rather than the random variable. Don't worry about that if it confuses you. So we use that trick. If I'm within 10 feet of you, you're within 10 feet of me. So in 95% of such samples, mu sub x, the population mean, is within that distance of x bar, the sample mean. In other words, mu sub x is contained in the interval x bar plus or minus 1.96 sigma x over the square root of n. That is a confidence interval for mu sub x. Perfectly good confidence interval. We can call it a day, except it's not very useful because it assumes that we know sigma. And the problem is we're trying to estimate mu, and it's very difficult to imagine a situation where you know sigma but don't know mu. It comes up, and occasionally this is a useful formula, but very rarely. So we need, remember, we ran into this situation in lecture 19. When we were estimating p, we got a nice formula for the confidence interval, but the margin of error depended on the standard error, which depended on p, the thing we're trying to estimate. What we did in that case was replace p with our best guess as to what p was from the sample, p hat. So we replaced p with p hat, and then we had a rather subtle argument that that didn't make much difference to the standard error and therefore to the margin of error. We're going to do a similar thing here, but we don't get the subtle argument. So, natural thing to do is replace sigma, which we don't know, with the sample standard deviation, which we do know. Sample standard deviation is the best guess point estimate for population standard deviation. So, that's a reasonable replacement, but unfortunately it is not true that S is usually quite close to sigma. In fact, that is true if n is really large. If you have a big sample, the sample standard deviation is a good approximation of the population standard deviation. But if you have a small sample, then it can differ substantially. What does that mean? That means, well, if we use sigma, 95% of intervals would contain the thing we're looking for, mu. Because we're using S instead of sigma, we're adding uncertainty. Sometimes the interval is too big, sometimes it's too small, which means that fewer than 95% of samples will give you intervals that contain mu. The cost of that uncertainty is that our confidence has dropped. So to get a 95% interval, we need to make the interval bigger. Right? And the more certain you want to be the interval contains the value, the bigger you have to make the interval. So we're going to replace 1.96 with a bigger number to take into account the uncertainty that we added by replacing sigma with S. That's the basic logic. Remember, 1.96 was the z-score, the critical z-score. We called it z star sub c. This was the case c was 0.95, 1.96. In general, we use z star c for different confidence levels. So this larger number we're going to replace z star c with, we're going to call t star, the critical t-score. But now, it doesn't just depend on the confidence level c, it also depends on the sample size, because we know for a big sample size it's pretty close to z star, because there's little uncertainty added, but for a small sample size it's going to be much bigger. So t star will depend on the confidence level c and on n. For historical and subtle reasons, instead of expressing the dependence as depending on n, we express it as depending on n minus 1. We call n minus 1 the degrees of freedom, and we talk about t star of c comma n minus 1, so that it depends on the degrees of freedom. We'll meet degrees of freedom a couple of times in the course. If you go on in statistics, you will understand what the common theme is that makes us call this quantity degrees of freedom, and it will become a close friend. But in this course, it will just be a somewhat awkward acquaintance. So that is not to worry about, but the important thing to know, I haven't told you how to compute t star yet, but the important thing to know about it is that t star is always bigger than c star, much bigger if n is small, and just a tiny bit bigger if n is large. What do I mean by much and tiny and small and large? Well, I'll give you one example. In the example we talked about, n was 50, and we wanted a 95% confidence interval. So that means our degrees of freedom is 49, n minus 1. Okay, so we say there's 49 degrees of freedom in this problem. So we need t star sub 0.95 confidence level, comma 49 degrees of freedom, and that turns out to be 2.01. As I said, just a little bit bigger than 1.96 because n equals 50 is a fairly large sample. So to recap, I still have not told you how to find t star c, but once you know it, you can get a 95%, or in general a c, confidence interval, whatever your confidence level C is, for the average value mu sub x of x in the whole population, and the confidence interval is x bar, point estimate, plus or minus t star times s over the square root of n. S has replaced sigma, t star has replaced z star, and the two replacements together leave you with a perfectly good confidence interval. So in our example of haircut costs, we had a sample of size 50, we had a sample mean x bar of 35, and a sample standard deviation s of 30. So we conclude that the 95% confidence interval for the average haircut cost of all college students is 35, that's x bar, plus or minus t star, in this case 2.01, times s, which is 30, over the square root of n, which is 50. And that works out to 35.0 plus or minus 8.53. It's not a percentage. Don't get confused and start moving the decimal place around. That's, in fact, dollars in this case, because we're estimating a quantity in dollars. And remember, as always, I just expressed the confidence interval in a complete sentence, which includes the confidence level 95%, the parameter, average or mean, because it's a numerical variable, the variable, which is the cost of the haircut, the population, all college students, the point estimate, which is 35, and the margin of error, which is 8.53. So again, we're following that template of how to report confidence interval. So, the one thing I haven't told you, where do you get t star from? 3 answers. The one that counts really is the third. First of all, if you look in the back of our textbook, if you have the textbook, there's a table. In that table you can look up, it's called critical t-values, and you can look up the value of t star based on the confidence level you want and the degrees of freedom. That's a fine way to do it, but it's kind of labor intensive when you have a computer. If you have a computer, you can use Excel. Of course, there's an Excel command that gives you the critical t-score, and of course it has a confusing and unmemorable syntax. The name of the command is tinv, T-I-N-V. That should remind you of the command norminv, which we've used before. You give it 2 inputs. One should be the confidence level, but just to keep you on your toes, Excel wants you to put in 1 minus the confidence level. So if you want a 95% confidence interval, you have to put in 0.05. If you want a 99%, you put in 0.01. And then the second thing you give it is the degrees of freedom. So if your sample size is 100, you put in 99. If your sample size is 7, you put in 6. That will always work whenever you have access to Excel, which I hope is true for the rest of your statistical life. But in fact, we won't use that. Well, we won't use it directly. We'll use a template that has that command built into it, which is called the T-procedure template. Whenever in this class I ask you to compute a confidence interval for a mean, you will be able to use the T-procedure template. When you leave this class, it'll still be on the web, you're welcome to use it, but you will probably, in any given context where you need to compute a confidence interval, you will have some kind of software, which you will have to learn, but it will work quite similarly. A few words about where this t-score comes from before I show you the template. The t-scores come from a distribution, a standard distribution called the t-distribution. Statisticians tend to refer to standard distributions like the normal distribution by a letter. The normal distribution is called the z-distribution because of the z-scores that are related, so closely related to it. So this is the t-distribution. It's a standard distribution, just like the normal distribution is defined by some complicated formula with exponentials and square root of pi in it. T is defined by a complicated formula with all kinds of cool math in it, which sadly we will not discuss. But its definition is it's the distribution of the quantity x bar minus mu sub x over s over the square root of n for any normal variable x and all possible random samples of size n. What does it look like? It looks sort of like the normal distribution. It's bell-shaped, like the normal distribution, but with fatter tails. So here you see a graph of a normal distribution, specifically with mean 0 and standard deviation 1. That's in black. And you can think of the normal distribution as the t distribution with infinitely many degrees of freedom, if you like. That's why it's labeled r equals infinity. But superimposed, you also see the t distribution with 6 degrees of freedom in blue and with 3 degrees of freedom in red. You'll notice the t distribution, similar shape, but fatter tails and less substance in the clump. The tails are much fatter when the degrees of freedom is low, like when r equals 3, and a little bit fatter when the degrees of freedom are a little bit bigger, like r equals 6. If we had done r equals 50 on there, or 49, the distribution we wanted, the tail would be ever so slightly fatter than the normal distribution. So that's what it looks like. I have to tell you the story of where the t distribution came from, because it's a great story with two ingredients, secret identity and beer. The inventor of the t distribution is William Gosset, or discoverer if you like. He worked at Guinness, the beer company, and he was doing what we in modern terms would call quality control. He was interested in making sure that all their processes for producing the beer were working exactly as intended. At the time, statistics was in its infancy, and people would take samples, and all the issues we worried about with replacing sigma with s, no one worried at all. And they covered up this lack of concern, lack of thoughtfulness, by just using really large samples. If you use large samples, you can replace sigma with s, and there's no big deal. The problem is, if you're doing quality control, you take a lot of samples. You're constantly taking samples of your process and making sure that everything is right. And if you take a lot of samples, and they're big samples, then you're wasting a lot of beer, which Gosset didn't want to do. He wanted to take small samples, as small as he could get away with. So he figured out how to do his calculations with small samples, which meant he had to worry about the difference between s and sigma, which meant he had to come up with this t distribution. These t distribution methods worked so well for him, he wanted to tell the world, but Guinness said, no, you can't tell people about your techniques because we're afraid some rival beer company will use them and outcompete us. So he published them nevertheless. He published them under the rather humble pseudonym Student in 1908, and to this day you will occasionally hear somebody refer to the distribution as Student's t distribution, which seems like a shame that Gosset never gets the full credit he deserves. Alright, here's how to use the t-procedure template. I am going to explain how to use it to you, and that explanation won't be very helpful. And then I'm going to show you how to use it, and that will be helpful. But I want to go through the explanation so that once you know, if you forget something or need to be reminded, it will be right here, and you can run through it. The basic procedure is you go to the templates page of my website. This is exactly where you went to get the histogram template. And in fact, the histogram template is at the top of the page, and right underneath it, there's a rectangle with a bunch of templates. We'll use many of them this semester. It's organized by rows and columns. The type of variable that you use is in the column. The number of populations or samples you deal with are in the row. So your first column is categorical variables. The second column is numerical variables. And the third column, which we'll never deal with, are ordinal variables. We're interested in a single population and a numerical variable, haircut costs or whatever. So you will see that under the second column, first row, is the procedure one sample mean, or T procedure. Statisticians love to refer to their procedures by the letter name of the distribution used, which isn't very helpful. So I will call it both the standard name T procedure and the more helpful one sample mean procedure, because we have one sample and we're estimating the mean. When you click on that and open it in Excel, it will look rather like the histogram template. In particular, there are several tabs at the bottom. One of them, just like in the histogram, is labeled Data. That's to the far left, and typically that's the one it will open in. Most of the time, when you do one of these problems, you will be given the data in the sample. You'll be given the data distribution, in which case you go straight to the Data tab, you click on column A, and you paste your data in, exactly as you would for the histogram. This is nothing new. Occasionally, you will not be given the raw data, the data distribution. You will only be told the sample mean, the sample standard deviation, and the sample size n. In that case, and I'll show you an example of this, you click on this second tab, which is called t-test. At the top of it, there's a spot to enter manually your mean, your standard deviation, and your sample size. And once you do, you have to be sure to check the little checkbox that says Use Summary Statistics, which tells Excel to look there rather than look at the raw data that's in the Data tab. Once you've done that, either entered your data or entered your summary statistics and clicked on the checkbox, all you need to do is in the middle of the page, of the t-test page, there is a spot that says confidence level. It defaults to 95% because that's the usual confidence level. You can set it to whatever you want. It's a percentage, so if you want 90%, you type 90 in. And as soon as you've done that, there is a green box to the right, which will show the confidence interval, both in the plus or minus form and as an explicit interval. That's all you need to do. Occasionally, online questions, which are expecting you to do all of this by hand and by table, will ask for intermediate calculations like the standard error, the margin of error, the sample standard deviation, various quantities, the critical t-value. Anything it will ever ask is listed below where it says confidence level, and you can just read those off. Finally, we'll come back to this. There is a tab labeled Hist, the third tab. It contains a baby version of the histogram template, so you can get a quick look at the histogram of your data distribution. We will use that to check the third assumption. I'll come back to that. So let's do an example. Let's look at the file in the data page of my website, floridastudentsurvey.xls. In column H, there's information about the hours, that's supposed to be a TV, sorry for the typo, hours of TV each student in the sample watched. It's a sample of Florida college students. Let's use that to compute a 90% confidence interval for the average hours of TV watched per week for all Florida college students. So I'm going to lead you through that now. Let's see how this works. We'll go to my web page, MA217. We're going to click on Data Files. And if we scroll down, here's floridastudentsurvey.xls. So I'm going to open that up in Excel, and I'll need to click on that. This is a survey of students at a Florida university. We'll take it as a simple random sample. And sure enough, column H, labeled TV, asks, just like I asked you in the first day, how many hours per week of TV did you watch? I don't remember if I asked that. I asked several questions like that. And we're going to copy this data, just as if we're going to make a histogram. So I click on the letter H, and I type, because I'm on a Mac, I typed Command-C. If you're on a PC, type Control-C. And now that's all we need. So we'll go back to the web page. We'll go up, using the back button, to the main page. And then we want a template. So we'll click on Excel Templates. And you remember this ugly page with histogram at the top, and underneath a little box labeled Single Variable Procedures. And the columns, you can have a categorical variable. That's qualitative, remember. You can have a numerical variable. That's quantitative. You can have a ranked variable. We're not going to talk about that, don't worry. And we will learn for the course of the rest of the semester how to deal with a single population from which you take a single sample, how to deal with two populations, two samples, and how to deal with many populations. We'll also learn how to deal with linear regression from an inference perspective. But right now, we have a numerical variable, which is hours of TV watched. When you ask each individual, how many hours of TV do you watch? One sample, so we'll use the one sample mean, or T procedure. When we click on it, we get another Excel file, which I will have to select. And here comes my T procedure. It has several tabs on the bottom. If you don't see those, you should, in a Mac, press the plus, and in a PC, I don't know the key code, but you should go up to Windows and select the thing that puts the window in a reasonable frame. And here are the three tabs. Data, which is just what you remember from the histogram tab. T-test, that's a new one. And hist is similar to the histogram page. And just as in the histogram page, there's dummy data already here. You're going to paste over it. So all you do is copy your data, open up the template, and paste your data into column A of the Data tab. So far, this is exactly what we do for the histogram page. Now comes the difference. We're going to click on that T-test tab, and you can see this pretty gray screen. There's a bunch of stuff up here, but in the middle, where it says confidence interval in green, there's a confidence level. It's set to 95%. We wanted a 90% confidence interval, so we're going to replace that with 90%. As soon as we do that, we get the confidence interval, 7.27 plus or minus 1.45. Here it also gives it to you as an interval, between 5.82 and 8.72. If you're doing this in the online homework, they may ask you for X bar, or the sample standard deviation, or N, or the standard error, or the critical t-value, and those are all right there. Okay? I will show you this in a moment. So 7.27 plus or minus 1.45 is what we need to remember. So let's go back to the lecture. And sure enough, the 90% confidence interval for the number of hours of TV watched is not on the screen, but it is 7.27 plus or minus 1.45. Okay, just like in lecture 17, we have to check the three assumptions. So this procedure is only valid, only gives you a 95% confidence interval, which is really contains the correct value 95% of the time, if the assumptions are valid. Three assumptions are exactly the same. There's a little bit of a difference in how you go about checking the 0, 15, 40 rule. So, first assumption, it's a simple random sample. In general, the problem has to say it's a simple random sample, or the answer is we don't know, or it's not met. If the sample method is described, then you can decide whether or not it's a simple random sample, and you can say. But if it's not described, it's just a question of whether or not it says. Large population rule, same as ever. You need the population to be at least 20 times the sample size. Usually that's obvious, but not always. The 0, 15, 40 rule. There's a little bit more care here. So still three options. The first one is still x has to be known to be normal. So that's only met if the problem says that x is bell-shaped. Remember, x, the distribution of x, is the population distribution. So if the population distribution is bell-shaped, you're done. It doesn't help, I should say here, if you look at the histogram and decide that it's normal, that doesn't make any sense, because you cannot tell whether a distribution is normal from 10 or 20 or even 30 or 40 data points. So it makes no sense to say I'm looking at the distribution and it looks normal. All you're seeing on the histogram page is the data distribution. You can't infer normality unless it's a gigantic data set, in which case you don't need to. What you can do, the second assumption, remember n has to be at least 15, and your variable has to be not too skewed with no major outliers. It turns out, by the magic of statistics, that if n is at least 15, then high amounts of skewness in the population distribution will almost always show up in the data distribution. Okay? So, in case 2, if you don't have a large sample, if it's not more than 40, and you're not told that it's normal, then you look at whether the sample size is at least 15, and if it is, then you look at the histogram. And then, if the histogram is not too skewed, you've met the assumption. Rule 3 is the same as always. If n is more than 40, we're done. So in the example I just did, the first example we talked about, when n was 50, no problem. Meets the 0, 15, 40 rule. The example we just did, Florida, the sample size was, I think 60 or 70, no problem. Assumption is met. Okay, so I want to say something about the 0, 15, 40 rule, which people understandably have a hard time remembering. It's a rather subtle point with a lot of conditions, and for that reason, I have come up with a mnemonic that I will guarantee you won't ever forget, but there's a cost to this mnemonic, and the cost is you have to take my advice about what cool is. People are always coming to me and saying, Steve, how do I get to be cool? And here is my answer. My answer is, it depends on how old you are. You remember when you were under 15, and you know that when you were under 15, being cool was all about being known to be normal. It wasn't good enough to be normal. You had to be known to be normal. So if you're under 15, you have to be known to be normal. If you're between 15 and 40, where you are now, the sad truth, let's all admit it, is it really comes down to whether or not you look good. So if you're between 15 and 40, your histogram has to look good, not too skewed. Most importantly, if you're over 40, you don't have to worry about anything, you just are cool. So n greater than or equal to 40 is the last condition. I thought of this mnemonic on my 40th birthday, by the way. Alright, let's do an example. In the file anorexiafix.xls, columns C and D contain the weight of a sample of 17 anorexic teenage girls before and after family-based therapy. So, just to get you caught up, we're looking at anorexic teen girls. We have a sample who came into a clinic, and we're given, there's other things going on in this study, but these 17 girls were given a family therapy. They want to measure the effectiveness of the family therapy. Effectiveness, in the case of anorexia, can be measured in how much weight you gain. So they weighed the 17 girls before and after the therapy, and what you'd like to see is that they increased weight. If they gained weight, the therapy was effective, and how much weight they gained measures how effective it was. That seems reasonable. So what we're interested in, which is in column I, is the difference, which is the amount of weight they gained during the treatment. This is a special case of a general procedure called matched pairs study. So anytime you measure for each individual, you measure something under two different circumstances and look at the difference as your variable. That's called a matched pairs study. This is an important thing to recognize because the fact that you see two columns of data later on in the semester when we learn a two-sample mean procedure may make you think you should use the two-sample mean. But in fact, it's a simpler procedure than it sounds like. So we'll come back to this, the two-sample mean. Just want to warn you about this ahead of time. So we're going to look at column I, the weight gained for each individual. And we're going to use this to give a 95% confidence interval for the average weight gained for all anorexic teens under this treatment. So once again, let me break the lecture and go do that. So I am going to the main page and then data files. And I want anorexic.xls. I think I said we need the anorexic fixed because there was a little mistake in the anorexia file itself. And column I. So let's take a look here. FAM1 and FAM2 is the weight of each girl before and after treatment. So you can see the first girl came in at a horrifying 83.8 pounds and managed after the treatment to go up to the slightly better 95.2 pounds. So she gained 11.4 pounds. So the treatment was reasonably successful for her. On the other hand, if you look at the seventh girl, she started in at 76.9 and ended at 76.8. The treatment didn't help at all in terms of weight gain. So what we'd like to know is, on average, how much weight can we expect a girl who receives this treatment to gain? So we want the average of these numbers. So I'm going to click on column I and I'm going to copy it. Control or Command C. And then I am going to go back to the web page. I'm going to go up to the main page and down to Excel templates. And I'm going to click on the one sample mean procedure. I could reuse the one I had, but as I've said before, it's easy to mess things up if you do that. So that's a bad habit. Open it up in the Data tab. Taking a little time. And we're going to paste it into column A. And we want, I believe we said a 95% confidence interval. So we already says that. So the confidence interval is 7.26 plus or minus 3.68. Let's go see if I really did say 95%, which I've already forgotten. Yes, 95%. So let's make it big screen again. And sure enough, the 95% confidence interval for the average weight gained by anorexic teen girls under family therapy is 7.26 plus or minus 3.68. So we're 95% sure that a typical girl, the average of all girls under this therapy would be, they would gain somewhere between 3.7 pounds and 10.9 pounds, something like that. Now let's check the assumptions. Simple random sample? It doesn't say. In fact, where these girls came from is they were girls who came into a clinic for anorexic girls. So they're definitely not representative. These are girls who have enough of a problem and are aware enough of the problem that they came in for therapy. And that is a pretty obvious bias, which we'll talk about a little bit later. So that assumption is not met. Large population, no problem. We'd need there to be more than 340, that's 20 times the sample size of 17 anorexic teen girls in the world or the US. We don't know exactly what our population is, but sadly, there's plenty more than that. 0-15-40 rule, that's a tricky one. We're not told that the amount of weight gained by girls is normally distributed, so we can't use version 1. N is not more than 40, so we can't use version 3, so we are forced to consider version 2. So let's go do that. So if we go back to Excel, here's our t-test. Sure enough, N is 17. That's more than 15. So it's good enough if our data distribution is not too skewed. We can tell that by looking at the histogram tab. There's our distribution of the weights of the girls in our sample, weight gains of girls in our sample, and you can see I might call this very slightly right skewed. If you fiddle around with it a little bit, you may become convinced that it's right skewed. Here are all the quantities that we use to compute. That we are interested in computing for a numerical variable. You can adjust the bin sizes and play around. You will see it's slightly right skewed, but that's totally fine. So the procedure to check the 0, 15, 40 rule is as follows. If n is more than 40, don't think anymore, you've met the condition. If the question tells you that the variable is normal or roughly normal or something like that, no problem. And if neither of those is true, then if n is more than 15, go and look at the histogram tab and make sure that the data distribution is not too skewed, and then the assumption is met. Otherwise, it's not. And I'm pressing the down button, which won't work until we're in full screen mode. Okay, once again, let me stop and talk about what the 95% confidence interval means, and in particular what that 95% confidence level means. We've said this before in the proportion context, but it bears repeating. 95% is a probability. Probability is telling you what percentage of all things you're considering have some property. So what are the things? What's the process you're repeating in this case? And the answer is you're taking a sample. What that 95% means is your confidence interval is a procedure. You give it a sample, it gives you an interval. Different interval for each sample. And the claim is that 95% of samples give you an interval which contains the quantity you're estimating, the population mean or population proportion or whatever. So that's the sense in which your interval has a 95% chance of containing the actual value, but the value isn't varying. There is some number, which is the population mean, which is the average haircut cost of a college student. It's a fixed number even though you don't know it. And your interval, even though you're looking at one interval there, that's the thing that varies. Each sample gives you a different interval. The interval has a 95% chance of containing the parameter. This is confusing particularly with numerical variables. People think that the 95% confidence interval is telling you something like 95% of teen girls will gain this much a weight in this interval. No. It is about 95% of samples give an interval which contains the correct value. Alright, we are now done with lecture 20. In class I'll give you an example of using the sample statistics, which we did not do here. Here's what you should know how to do. You should be able to use the template to find a confidence interval given confidence level and either raw data, which is a column of numbers, or the mean, the standard deviation, and the sample size. You should be able to express that confidence interval in a sentence identifying the confidence level parameter, variable, population, point estimate, and margin of error. That's way back in lecture 18. That should be old hat by now. You should be able to check each of the three assumptions: simple random sample, large population, 0, 15, 40. That's also old hat back in lecture 17, with a slightly new wrinkle on the 0, 15, 40, because we can look at the data distribution. You should be able to distinguish between, very important, a confidence interval for a mean, that's lecture 20 with a numerical variable, versus the confidence interval for a proportion, which we learned about in lecture 19, that applies to a categorical variable. You should always stop and ask yourself, before you do anything else, am I dealing with a categorical variable, or am I dealing with a numerical variable? And finally, you should be able to interpret the confidence interval. Remember that the interval is the set of plausible values for the population mean. The confidence level tells you the proportion of all samples whose intervals produced in this fashion contain the population mean. That is all for this lecture. See you next time.